Before we dive in, I've got something for you. If you're studying for the ARE, you don't need to figure it out alone. Inside my free resource hub, you'll find study guides, resource guides, pop quizzes, and other tools designed to make exam prep a whole lot easier. Head to dci.beyoungdesign.com/resources or check the link in the show notes to grab it now. It's completely free. All right, enjoy the show.
This video popped up recently on Instagram and people were going wild. Like, what is going on? Why didn't people address this swaying and this happening? I mean, look at this crowd. You can actually see the entire stadium moving under their feet, and it's exciting for sure. Like, they're moving, but it's also pretty concerning. And people are like, well, obviously engineers and the people designing that, it's meant for it. It's meant for a crowd to be cheering. But the way that the crowd is cheering and the exact movement that is happening makes it concerning. So today I want to talk about why this movement is happening, not just because of the movement of the crowd, but also why the structure is moving in the way it is and when it can be dangerous. We're going to talk about why this is so critical for aspiring architects, for architects in general, and if you are taking your architectural licensing exams, this is also important to understand. All right, let's do it. When an engineer is calculating a structure, they are going to be calculating live load. There's dead load and live load. And live load is the things that are moving around or maybe aren't always going to be in that structure. So it might be people, might even be like vehicles, furniture, even wind, because it is not a constant happening on the structure at all times. So it is malleable. Now, the engineer does figure for this. They figure a certain amount of live load, and especially in something like a stadium, they're going to figure everyone in their seats. They're going to figure people chanting, people moving around. That is definitely going to be part of their calculations. And they're even going to buffer it a little bit, so giving them a little extra wiggle room. So here's where things can go wrong. First, if there is a lot of extra live load that is not calculated for. This sometimes can be seen on, say, like a roof that isn't meant to be used as like a roof deck. And then all of a sudden a bunch of people are on it and it's not designed for that weight. That can create failures. There's also certain situations where maybe it is the right amount of live load calculated for it, but the structure gets in a certain frequency that can create problems. If a structure gets in a certain movement that becomes equal to the live load frequency, so there's people moving around, for example, and they are in a certain frequency, and then you have the structure that is designed for a certain frequency. Here's the thing. You don't want those frequencies to be equal, because if they equal, then they get in something called resonance. And resonance is like a beautiful thing. It's something we want. Like, think of when you say you meet someone new and you're like, yeah, I don't know, something just didn't resonate with us. Like, we didn't really resonate. It's literally your frequency and their frequency, not in resonance. And so you repel each other. If you say, oh yeah, we really resonated, we really connected, right? It's usually your energy, their energy getting in resonance, getting in the same frequency and moving harmoniously together. That is beautiful. That's lovely. Resonance is a gorgeous phenomenon. However, when it comes to structures, it can be super dangerous. So let's talk more about what resonance actually is. So resonance is when there's a repetitive force, sort of like people jumping, or for example, in that one video, everybody jumping in the exact same rhythm, and it matches the natural frequency of vibration. What this does is it actually creates a feedback loop. Think of like a pendulum, right? Like you hit it, and once it's going in resonance, it's like nothing's gonna stop it. So it gets in this feedback loop that causes that movement to grow and expand. The problem with this, especially when it comes to structures, bridges, other things, sometimes that movement can then become uncontrollable. If it becomes uncontrollable, then it's in resonance. There's nothing that's really going to stop it until it fails, until it breaks. So we've seen this in a couple different bridge examples. We have seen this in some stadium examples, and it is something that, of course, engineers, when they're designing it, have to be aware of, but it's also something that if one tiny thing is wrongly calculated, things can get in resonance and it can create failures. This also we see sometimes with earthquakes, really strong wind events that add on extra vibration that wasn't originally planned for because it's an unpredictable phenomenon, then that can create that failure too. So in that stadium footage, is it safe? Most of the time, yes. Engineers do plan for that extra live load, for that big rowdy crowds, especially when it's like a stadium that they know is gonna get intense. But what we see in this video may be an example of resonance taking over. And I say this because you will see that the people in the stadium are starting to all jump at the exact same tempo. And then the stadium is moving. Now, what happens with resonance, and we saw this on the Millennium Bridge, it's like a back and forth thing, right? It doesn't necessarily just start with them jumping at the same time. It doesn't just start with the structure moving at a certain rate. What happens is they start to come into resonance. So you'll see this in a pendulum, for example. I mentioned pendulum earlier, but if you look at a pendulum and you make it erratic, like you don't intentionally have the balls going at the exact same frequency, you do it more erratic. Eventually, they're going to get in sync and they're going to start being in resonance. So that happens also with the structure. If a bunch of people are walking across a bridge, for example, they're not intentionally walking the exact same way, right? It's not like an army march or something. They're just walking, but then the bridge starts slowly moving. Well, the bridge starts slowly moving and the people start getting in resonance with that bridge or structure or stadium, whatever it might be. And so because of that scientific phenomenon where things will get in resonance, they'll get in the same movement as the things near them, then they start to actually sync up. And that's when we saw, like the Millennium Bridge, for example, normal crowd, normal people. You watch that video and people are walking as if they're army marching, right? They're walking in sync. They're all swaying at the exact same time. They're all putting their left foot down at the same time. Obviously, that wasn't planned, but that was them getting in resonance with this bridge. So especially if you're on a structure that starts swaying, that doesn't feel super comfortable, right? You're going to move to keep your balance. And in doing so, you're going to start swaying to keep your balance in movement with that structure. And so in doing so, you're actually amplifying that movement of the structure. You're feeding into it. It's amplifying, it's growing. It's kind of like pumping a swing, right? If you're on a swing, you get into the movement with the swing and you're pumping your legs to increase it. You're going to go higher. That movement, that wave pattern is going to increase. And that's when it becomes this big feedback loop that if done improperly or if not controlled, it can lead to that failure. So with the Millennium Bridge, they noticed, whoever, the engineers, the designers, or whoever it was, saw what happened, noticed that movement, noticed what phenomenon was happening, and they immediately shut down the bridge. Most engineers know and understand that you need to design, especially like a walking bridge, with a different hertz as a standard walking pattern. A human stride is typically 2 steps per second. Bridges can't have a vertical frequency of 2 hertz. Otherwise, they'll end up matching up, they'll get in sync, and then they'll create resonance. But the engineers ended up not calculating it a certain way. And then also once the people started moving in a certain way, it was a different bridge structure that they started doing. That was, a lot of the support was vertical. The people started moving in a different pattern, which then ended up matching that bridge. So they shut it down. They had been a huge disaster, to be honest. I mean, luckily nobody was hurt. The bridge didn't fail, but they had spent so much money building up, and like thousands of people showed up for this opening of this bridge, and it was literally shut down and had to be redesigned right afterwards. And we see this synchronicity all the time, like in nature. The idea of getting in sync isn't just for, people, or like I was even saying, like you resonate with someone else. It's not just with structures, but we see it everywhere, from fireflies that are flashing together. You'll see trees with fireflies in it and they will be all mismatched. And then once they're together for a little bit, they'll start in sync, flashing together. It's incredible. Bees buzzing in harmony. And then, of course, we see it in the pendulums. The pendulum is just like the most easy, automatic way that we can visualize it and see what that resonance really means. And looking at how this synchronicity happens so naturally in the world helps us understand how that can also happen in our man-made structures and why it is so critical to properly calculate those frequencies, that movement, those hertz, so that they're not in sync, so that the structure stays strong, the people can move, and that's where live loads are super important. So for aspiring architects, understanding these different structural concepts like live load, dead load, resonance, dynamic loads, these are all really critical. Even though structural engineering is going to typically be handled by licensed engineers, architects need to know how to coordinate with these engineers and ensure that the building maintains safety standards. Also, if the engineer recommends something, we have to understand what that means and then why that is important. And also we can do our due diligence of recommending or checking in on certain things to make sure we have the safest design possible. So you might see something like this in the ARE 5.0, and it might, particularly in PPD, project planning or design, and PDD, project development and documentation. So on the exam, you may see questions about how occupant loads affect things like maybe egress, or how dynamic forces like wind or vibrations or even rhythmic movement impact a building, whether it's the framing or the foundation or even earthquakes, and how we can design structures to withstand them, not only withstand them, but to also address them before they even happen. So for example, earthquakes, we don't want our building to get in resonance with the ground shaking. When the ground shakes and the building is on it, right? And the building starts shaking, well, then it just gets in resonance, right? It gets moved, and that's where we see a lot of failure in buildings. So in high earthquake areas, they will, for certain buildings, depending on like the height and whatever it is. So first of all, there's lots of different things that you can do for earthquakes to brace from them. So this is just one item of it. There's all sorts of ways, but the one that I was going to mention is base isolators. And this is literally like in a high rise or something in the basement, they literally have these giant base isolators that allow the ground to move without having the building move with the same resonance as the ground. So it's isolated, which will allow it not to get in resonance. You're not going to have to solve formulas in depth or anything like that on the exam, but you have to understand the concepts and really understand how they affect a building and why in certain areas, like again, wind or earthquakes, how the buildings need to be designed in areas like that in order to withstand this concept. Again, architects' role is always to protect the health, safety, and welfare of the general public, and this is part of it, designing safe buildings. And again, with the coordination of our consultants like engineers and whatnot, but we still have to understand it. And we have to also help design it. For example, what sort of shear walls we're going to be including, what kind of structure design we want to include so that we can design something that's beautiful that also works with what the engineer needs to do too. And one way that you can also remember this, with the bridge examples, is that they actually require soldiers to break their stride when they're crossing bridges. If you can imagine a line of soldiers, they're always walking in sync, but if they're crossing a bridge, they are required to break that sync so that the bridge does not fail as they're walking over it. So, back to the original stadium, the real concern isn't just the cheering, it's not the jumping around. That would have been calculated, but it is the fans cheering in unison. It's them jumping up and down in the exact same pattern, having that stadium start moving, and then them increasing their jumping and increasing their unison. So, increasing it, so then that increases the movement of the structure. Those are getting in sync, those are balancing, and that resonance is really growing. This doesn't mean that the stadium is going to fail or collapse tomorrow, but I would say it does question the design and safety margins on this. And if I were a local engineer or if I were the designer of this stadium, I would definitely be looking into this to make sure whatever we can do to help prevent that from getting too escalated and having a future collapse. But again, I'm just an architect. We rely on our engineers to do the right calculations so that there aren't failures. You know, as architects, we have to know a little bit about everything, but we only know so much. So if you are an engineer, I want to hear what you think. Do you think that this could actually lead to a failure? Let me know in the comments if this is something that you would be worried about as a engineer on this project, or if it's all part of the calculated design and it's nothing to worry about. And for you aspiring architects who are taking your exams, remember the differences between the live loads, the dynamic loads, the static loads, all the different loads that can happen on your building, how they impact your design, how you can design to resist them, but to also design to prevent failure. It can show up in the exams and also in future projects. I mean, I'm in California and we have to design for earthquakes all the time. So it is super critical for you to understand the concepts, understand the concept of resonance so that you can stay on top of it. All right, if you found this video helpful, please like, please subscribe, and also let me know if there's any other topics that you would love me to cover in the future. Thanks for watching, and while you're waiting for our next episode to come out, check out this video next.
Thanks for listening today. Hey, remember, you've got free resources waiting for you at dci.beyoungdesign.com/resources. And when you're ready for deeper support and to come hang out with us, join us inside the ABC Club and ABC Club Premium, where you are going to get the help you need to pass your exam and actually enjoy the process. So don't let another week go by without moving forward. Take action. You got this. Check the links in the show notes and join us inside the club.